All right. Hello, everyone. Happy September. Hope you had a nice weekend. Hopefully, you did the quiz. If you missed it, something I might do for this week, I'll just say it. For this quiz, because it's the first one, I will give an extension. I haven't gotten any emails about this, but I know how this goes. The first one people always miss. I will give an extension till tomorrow at midnight for quiz 1. If you did it, awesome. You don't need to worry about it. I won't do this for any future quizzes, though. I'm doing it for the first one because I know how this goes. The first one, you're getting used to the class structure. But all future quizzes, so quiz 2 is due this Saturday. Remember, keep track of these. It might not seem like a big deal. Each of these quizzes is worth about 2% towards your final grade, which might not sound like that much, but it's going to sound like a lot if you have an 88 in class, or if you have a 78 in class, if 2% adds up. If you miss a quiz, so one quiz is dropped, so yay. But something to keep in mind in all your courses, whenever there's assignment for a certain percentage. So in our course, the quiz are worth 2%. So if you miss a quiz, again, one's dropped, let's say you miss 2 quizzes, then the highest grade you can get in the class is a 98. You miss 2 quizzes, the highest grade you can get in the class is a 96. Anytime you will miss points, that automatically reduces the highest grade you can get in the class. That's the mindset to have when it comes to assignments and jobs and things like that. Deadlines are important. So anywho, great. I'll do that extension sometime today to Wednesday. Haven't gotten any emails about it, but I bet if I look, there'll be a non-zero amount of people that missed it. So, great. Quiz is due. Recitations are happening. All that jazz. I think that's pretty much the same old. So, concept-wise, last class we started talking about finding electric fields and setting up integrals. So the quiz that is due this Saturday has a problem where you need to know how to set up the integral. The answers are all which of the following is the correct integral. So I give you some situation. And there's a few variations on the problem. I'm not going to tell you what the problem is, just so you see it. I try to tell you what it is. It's a finite line of charge, not infinite. And I say, what's the electric field at some point above the left? Most part of it. And I give that a charge distribution. I say that the charge density is either 5x or 5 over x. There's variations of these. One of the variations of the problem says, what's the integral for the x component of it? One of them says, what's the integral for the y component? You'll notice the answers have positives and negatives because when they're pointed up, down, left, right matters. So if you're finding the x component and it points to the left, that's negative. If you're finding the y component and it points down, that's negative. Direction matters, yada yada. Great. So this is a skill. It's one of those skills I want to teach you all. We're going to keep seeing integrals and things like that. I'm not stressed so much on whether or not you know how to do trig substitution. You got a whole class on that. I'm not going to make you do that in the test. Or things like that. It's just not worth the time for us. We don't have the time on a test to do that, but you need to know how to set up the integral. So we did 2 cases. We had the straight line of charge, and we did that. And then in the last 5 minutes, I set up this one. I didn't solve it, but we got pretty close, where we found that instead of just doing lambda dl, where dl, so in the 1D case, dl got replaced with dx. So we made the substitution that we had lambda dx, yay, and that gave us the amount of charge in the tiny little part. Here, we did this dl equaled r d theta. It's called arc length. If you want the arc length of something, it's r times theta. Make it d theta. Great. This is a good one to go through. This one, ironically, is easier than the other one, but you got to know about arc length. You got to know about this whole arc length substitution thing. So these are the 2 cases I kind of went through with you all. And that closes us up on electric fields. You got to practice these, try these. There's one more problem. The problem set I didn't go through, but reminder to you all, you need to start these problems with a blank sheet of paper. If you can't solve these problems with a blank sheet of paper without a guided solution next to you, by the time the test comes, well then, what if it shows up on the test? You're not going to have those guided solutions next to you and all that jazz. Your note card will not save you on a test. Your note card might give you a little bit, might help you get over some small speed bumps, but it is not going to give you every answer you need. Which is why I let you all have a note card. Because it just helps you with memorization stuff. It's not going to teach you the process. If you don't know it, you're not going to have time to learn it during the test. All right, great solutions here. Last thing is, what are some variations on these? I could make the line of charge finite. That's what I did on the quiz coming up. I could do a quarter loop instead of a full loop. I could make a charge distribution a function. This is also what I did on the quiz. You need to be able to build the integral regardless of what I do. Solving the integral I'm not super worried about because it's actually really difficult for me to give you all problems where the integral is not awful. So building the integral, though, is very easy for me to make problems for this. Great. Okay, so that's that. That finishes up last week. So this week, our goal is to learn something about Gauss's law. It's another way to find electric fields. So we're going to hopefully finish that up today. And then on Thursday, we're going to start talking about something called electric potential, which is another name for voltage. So we're going to start with electric potential energy. Then we're going to get rid of the word energy. We're going to figure out how to go from that to electric potential, and then get into voltage. And voltage is one of those things that you have definitely heard about. It comes out of, wall sockets. You got 120 volts coming out, 110 to 120 if you're in the US, 230 to 240 if you're in Europe. So that's where we're going to start getting into voltage, which will then lead us into capacitors and circuits. We won't get to circuits in the first test. So the first test is going to be electric fields and voltage and electric potential mainly. We'll also have capacitors and resistors in there, but honestly, that's going to be like the easiest thing I teach you all. Yeah. Electric force, yes. Yeah, sorry. Electric force will also be in there. Electric force, electric fields, voltage, electric potential energy, all the things in the syllabus. So, yeah, let's go ahead and jump over to Gauss's law and get started on that. Gauss's law is, I spent a decent amount of time when I was making these slides. It's called a law. So the really funky thing with Gauss's law is called a law, and I've told you all laws are based on observations of reality. But the really funky thing about Gauss's law is it's almost derived from Coulomb's law. So Gauss's law is actually it's going to be about electric fields. You can't see electric fields. You can't observe electric fields. You can't count them. We're going to be, quote unquote, counting electric field lines, which you can't technically do. So Gauss's law is a funky thing. It's called a law because it's based on Coulomb's law. But my goal is going to be to convey to you all what this law does, how it's useful. It's one of the 4 equations that shows up in Maxwell's equations, which you may or may not have heard that phrase before. We're not going to get into too much of this class, but Maxwell's equations are the 4 equations that basically describe all of electricity and magnetism. With 4 equations, you can basically describe everything with electricity and magnetism. And this is one of those equations, which is why I'm teaching it to you all, because it's pretty foundational. So, to do so, we need to talk about what electric flux is. That's going to be a new phrase. It's not going to be anything crazy. It's just got a funny word to it. Flux.
Isn't it often like execution?
Yeah, that's the one that's often mentioned too. Is Back to the Future, the movie, the quantum flux capacitor, whatever. It's one of those buzzy words. It just means the flow, how much stuff goes through something. The flux is like the how much stuff goes through something. We'll see that. And then we're going to use that in Gauss's law, and it's going to be a grand old time, and it's going to let us find electric fields. That's the end goal. Gauss's law is a tool that lets us find electric fields due to situations where if we try to do it the way I just taught you last class, it would be an absolute nightmare. So, all right. First, we need to find something called electric field lines. This is not like a new thing, but we're going to just, some things I need to mention. So electric field lines are those like arrows that we draw away. Everything with charge makes electric fields around it, makes electric field lines. It's a way of visualizing how strong the field is. The closer the lines, the stronger the field. So remember that every object makes an electric field everywhere. And if you kind of connect those lines together, we get these electric field lines. So, in the easiest case I can give you all, which is, this is going to be devastating. I left my pen in my office, so we're finger painting today. So there's a positive charge. And remember I told you how it makes electric field lines and they get weaker and weaker and weaker? The idea is that we just connect all of these lines together. And the difference here is the closer they are, the stronger it is. So we're not so much looking at how big the arrows is. We're connecting all these arrows together. They get curved, because some will point down to the right, some will point flat, etc., etc. And we just connect them all together, and it shows us what the whole field looks like. Great. Nothing crazy, just another way to visualize it, but we're going to use this idea to explain some things. If you want the field at any point, so say I'm up here at the top of this positive and negative charge, and I have this like curved thing. If I want the field up here, I just draw an arrow tangent to it. If I want the field over here where it's kind of bent, again, same thing, I draw the field tangent to it. So if you want the field at any point on these curves, draw a line tangent to it. How big do you make that arrow? Well, you can't tell that from the picture. Well, based on how far away how tightly packed they are and stuff like that. Cool. All right. Another idea that's going to not be anything crazy, and these are all the logical steps that the person took to come up with Gauss law. The more charges we have, the more lines we draw, because the stronger the field. More charge, more field, more arrows. That's the idea. We're going to use all these together. So you can see here when I have a little bit of charge on the left, there's only 1, 2, 3, 4, 5, 6, 7, 8 lines. Here, when I have more charge, I have twice as much. I draw twice as many lines. Twice the charge, twice the number of lines. 3 times the charge, 3 times as many lines. It's just a nice way to visualize and see these things. Great. So, Carl Friedrich Gauss, he came up with this law. So this is basically the statement of the law. It says, this is one piece of it. If you draw a bubble around some charges, the number of field lines going through it is proportional to the amount of charge you have. It's kind of what we just said. More charge, more lines. And so the thing that happens here is he said it doesn't matter what shape you draw. So say I have some charge here. Again, these are going to be ugly pictures. And it has a certain number of field lines going through it. Yay. Let's say it's 4. And then let's say we have one over here that has twice as much charge. So it gets 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. This is hideous, I know. If I draw a crazy bubble around it, so let's say, nope, not that. If I just draw something odd, it doesn't matter the shape. However I draw that, 4 arrows go through it. Doesn't matter what that shape looks like. Doesn't matter whether it's a perfect sphere. Doesn't matter if it's a weird, crazy shape. 4 arrows go through it. Even if that loop did something weird that went back on itself, we also say if it goes out of it, it's positive. If it goes into it, it's negative. We'll see that in a second. And so the same idea over here. If I draw some crazy shape, I don't care what shape I'm drawing, I get 8 lines. More charge, more lines. This is the logical process he followed to come up with this law. Direction matters. So if I'm going out of the shape, if my lines are going out of it, we call that a positive flux. If the arrows were instead going into it, we call it a negative flux. Just because direction matters. Direction matters. And it helps all this stuff kind of work out. You may be like, why would it go into it if I had a negative charge? If y'all remember, negative charges make field lines pointed inwards. So this one, through some random shape, would have a flux that's negative because it's pointed inwards. Yeah. So this is the first kind of law. More charge, more field. It's not a crazy idea. He's not saying why. He's just saying this is a reality. And this again connects to Coulomb's law, and so it's all based on observations of reality. That's why it's a law. All right. So here's a picture. What is the electric flux through this closed surface around the following charges? When I'm saying flux here, I'm literally saying count the number of arrows going through it. If the arrows are going outwards, you count that as a positive. If the arrows are going into it, you count that as a negative. That's all I'm asking you to do here. Don't worry about the units right now. Yeah. Clickers are going to start mattering today, yeah. So hopefully everything's working for y'all. If not, I'll continue to work with you. But after today, all the other ones I'm going to delete, and we'll start syncing them over. All the old ones get deleted. Moving forward, all these matter. Now remember, to y'all, if you miss a question, it doesn't really matter. What matters is that you answered it. 80% of the points for answering it, 20% for getting it right. At the end of the semester, I graded out of 80% of the points anyway. All right, yeah. Yeah, so I'm going to go ahead and send this question, but the question is, what is the electric flux? How do you find electric flux? Count the number of arrows. If they go out, that's a positive 1. If they go in, it's a negative 1. So when you're counting, outwards is positive, inwards is negative. And you got a positive and negative charge here. I'm going to zoom it. The answers are, is it 16, positive 16, negative 16, positive 8, or 0? All we care is if the arrows point in or out. So you count if the arrow passes through it and it's going outwards, positive, if it pointed inwards, we only care about the interface. Yeah. It doesn't even pass through that surface, that red dotted crazy shape right through. It's going to touch the red dotted surface. That's where you're counting. You're counting at the interface. All right, give y'all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so this is a kind of, so this problem I am giving this is a simplification of it, but it gets the idea across. So that's where we're starting with this one. So we just count them. This one's out. So again, we only look at the interface. So this arrow here on the bottom left, that's positive 1, positive 2, 3, 4, 5, 6, 7. This one's going in, so we go down by 1. So this counts as a negative here because it's going inwards. So just to clarify, we got 1, 2, 3, 4, 5, 6, 7, 8 outwards on this side. 1, 2, 3, 4, 5, 6. So actually, yeah. 1, 2, 3, 4, 5, 6, 7, 8 outwards. 1, 2, 3, 4, 5, 6, 7, 8 inwards. So positive 8 plus negative 8 is 0. What's the flux to this surface? 0. Every field line that goes out eventually wraps its way back and comes back inwards and it's 0. Think of it like a flow. The amount of arrows flowing outwards equals the amount of arrows flowing inwards. Now, this then gets us to a very important concept. If this is positive Q and this is negative Q, how much charge is inside this? 0. So that's another thing Gauss's law said. Remember, the amount of flux is proportional to the amount of charge. The amount of flux I have is proportional to the amount of charge. How much charge do I have? 0. Multiply 0 by anything and you get 0. 0 flux because there's 0 charge.
How come we're not worried about the arrows not in the...
We're only worried about this closed shape we draw. So that's the key part here that he said. If I draw some random shape around it, the amount of flux going through it is proportional to the amount of charge in it. Yeah. The charge inside this bubble is 0. Positive and negative, if you added up that total charge, it's neutral. The net charge is 0. Yep. All right, so here's the formal math definition of this, and it's going to have a little bit more fanciness to it. So how do we determine this flux in a mathematical sense? Well, we both care about the field, how many field lines. How do we do that? We have a way to calculate electric field. We call that E. And then we care about this shape, the interface. So that's like the area of it. So this flux, this is the fancy symbol for it. It's called phi. It's the Greek letter phi, the capital Greek letter phi. It's a circle with like this kind of I crossed through it. So this is the symbol for flux, electric flux, equals E dot A. The electric field with the dot product of the area vector. So the electric field vector we chatted about, no big, that's actually what we're going to be solving for in almost every problem. The area vector is something you may or may not have seen before. It's a very simple vector. If you want to describe a surface, you need a vector that can describe that surface. Now, if you have a flat surface, like for example this table in front of me, I can't say that the area vector points along the surface because there's an infinite number of arrows that point along the surface. So if I have a flat surface, I can't say like this the area vector points towards you all. It's like, it's a flat surface. So what do? The area vector is the vector that's perpendicular to the surface. The area vector is a vector that's perpendicular to the surface. That's how we define the direction of the area of something. If you know that, then you can describe what that shape looks like, regardless of what orientation you might be. And if you're like, how do I figure out the vector perpendicular to the surface? The trick I tell my students, you all, trick I tell everyone, is take like a pencil, put the eraser on the surface, and boom, you got the area vector. It's that easy. If you want the vector that's perpendicular to a surface, take a pencil, take a marker, take anything, just put its butt up against it, and boom, the pencil or whatever is going to point the area vector. So you can see here when I have a curved surface and I move around it, the area vector changes direction. When I have a flat surface, it doesn't change direction. Area vector points in the direction perpendicular to the surface. Super, super useful. Lets you describe what a surface, the orientation of it, mathematically in a way that people can understand it. Remember, that's the whole purpose of math. Explain logic. So, dot product. You all may or may not have seen a dot product before, but it's much simpler. So a dot product, there's a fancy mathematical way of doing it. We're not going to bother too much with that. You multiply the components and then you add them all together. I'm not going to get into that too much. What I am going to chat about is this other way of writing it. The magnitude of E times the magnitude of A times cosine of the angle between them. This is what a dot product is doing. And I think this helps make it really understandable when you use this notation as opposed to the other one. The other way is great. It's useful. All you're doing is multiplying the parts of the vectors that line up with each other. When you're doing a dot product, you are multiplying the parts of the vectors that are either parallel or anti-parallel, depending on their orientation. So, here's a beautiful picture of a flat surface. It has an area vector up to the right. It has an electric field pointed directly to the right. I can show you all this. If I take the area vector and I break it into components, if I want to find the component that is parallel to the electric field, let's call this AX. How would I find AX? I would multiply A times cosine theta. Again, I know this is hideous with my fingers, but it's better than nothing. So look at that. Oh, look, it's this term right here. When you do a dot product, you are literally taking two vectors, you're finding the part of one vector that lines up with the other, and you're multiplying that together. That's all a dot product is. Finding the parts that line up. How much of this electric field lines up with the area vector? And you can go the other way if you want. You can find the electric field that lines up with this. How much of the electric field passes straight through that thing, straight in a way that lines up with A, or you can find the part of A that lines up with E. You're finding how much of the field lines, so if I draw this a little differently, I can instead say how much of my field lines point in the direction of the area vector. How many go straight through that surface? How do you find that? E times cosine theta. That's what a dot product does. So back when you all did physics 1, you saw a dot product when you did work. Work is the integral of F dot dl. What are you doing there? You're finding the part of force that lines up with the direction you're going. Because that's going to speed you up or slow you down. You don't care about the perpendicular part. So, that's the logic. If that doesn't make any sense, that's okay, as long as you can kind of do it. That's what's important. So, this is the mathematical representation of flux. Cool. Technically, I should have made this an integral. It should be E dot dA. I think I might have that written somewhere. Let's see if this makes sense. I got an electric field here with a value of 100 newtons per coulomb. It's some really tiny writing here, so I wrote it up here. The electric flux through this square is what? So I have the electric field passing to the right through a square such that this is going to pass right through that square. So it's a sheet of paper, electric field is going left to right. My question is, what is the flux through this square? Is it 0? Is it 200 newtons per newton meter per coulomb, 400 newton meter squared per coulomb, or none of these? Based on that definition I just gave you, what is the flux? It's a good question. Oh, the square has size 2 meters by 2 meters. That's hard to see. The square is 2 meters by 2 meters. All right, give y'all 20 more seconds.
Wait, is the plane 90 degrees?
So the plane is like this piece of paper, and my field's going like this. It's up to you to decide what the angle is. So the paper is like my plane, and the electric field is going through it.
Okay, so cosine 90 cosine.
All right, and 5, 4, 3, 2, 1. So I'm going to approach this 2 ways. I'm going to approach this with our definition of flux, not mathematically, and then we'll do the math way. Remember flux. Flux is how much it passes through it. That's the idea of flux. It's how much passes through it. So in this case, my electric field is very much passing through this thing. I mean, if you got a hoop here, you got a sheet of paper, the electric field is very much passing through this piece of paper. Very much so. I mean, it's going through it. That's the idea of flux. Let's look at the math way of explaining it. The area vector points perpendicular to the surface. Boom, there's my area vector. So that's my area. My electric field also points that way. They point the same way. Remember, what's the definition? All this comes from what the definition of flux is. How much of it passes through that? This passes through this as much as possible. If you imagine that this is like a hoop, and you imagine this is like water, all this water is going through this hoop. A lot of water is going through that hoop. That's a great way of thinking about flux, is like this flow of something through it. If there's a hoop, a lot of water is passing through it. Why? Because they line up. So if you write out the math, so you got your sigma equals EA cosine theta. Oh, everything's so much slower. Ugh. Magnitude of E times the magnitude of A times cosine of theta. Great. What's the angle between these? 0. The area vector, it's 8. What's the magnitude of the area? 2 times 2, it's 4. This is 4. The other one's 100. So this is the only one with the right units, too. This is the only one that has the right units. And you're like, whoa, where did these units come from? They were on the last slide, but it's really easy to prove the units. The units come from what's the units for electric fields? Newtons per Coulomb. What's the unit for area? Meters squared. You multiply them together, and ta-da, you got flux. It's the only one with the right units, so that was also a nice little thing. 0 has no units. That's a nonsense error. What is 0? I don't know. You got to tell me what 0 what. Yeah.
Wait, so is the angle between the electric field and the area?
Yes. The angle, because at the end of the day, I want to see how much of this lines up with this.
That makes a lot more sense.
It's how much the electric field lines up with the area. Now, let's look at the other case. What if instead my piece of paper is flat? So same kind of situation. I got an electric field pointed to the right. Same exact sheet of paper. Same exact planes, hoop, whatever you want to describe it as. What's the electric flux to this one? And I gave them all the right units this time. Alright, give me 20 more seconds. You didn't draw your area vector, that's good practice. Alright, in 5, 4, 3, 2, 1. Alright, so first step is you can't draw your area. Again, there's two ways we can do this, conceptually and mathematically. If I have a loop of water that's kind of flat like this, and I pretend like this is water, how much water is flowing through my loop? None. Nothing is going through that loop. So you can see where this angle thing comes into play. When you're like lined up perfectly, you get all the flow. When you're flat, you get none of the flow. When you're in between, you're in between. How much of it lines up with that area vector? Now, mathematically, when you draw this area vector, remember, you just take a marker, you just take a pencil, and you put it flat on that surface. The area vector points either up or down. It doesn't actually matter. You can make the area vector either point up or you can make it point down. It doesn't change anything. At the end of the day, the angle is still going to be 0. So that's that. My angle is going to be 0. So the angle between the E and the A, sorry, yeah, correct, is 90. So theta equals 90. And boom. 0 flux. Nothing flows through this flat thing. All right. So there we go. And this one, I'm not going to... do I want... Yeah, sure. I'm going to make you all do this one, especially because my pen doesn't work. Same problem. But now, this is at a 20-degree angle. It's at a 20-degree angle to like this thing down here. So you might have to do some geometry, draw the picture. You can also use your concepts of flux to help you figure out what the answer should be. That's often how I do it. So yeah, is it 0? Is it 400? Is it 400 times cosine of 20? Is it 400 times sine of 20? Or none of these? Sine of 20 equals cosine of 70, in case you're like, whoa, where's sine coming from? All right, give you 20 more seconds. All right, in 5, 4, 3, 2, 1. So, again, we're going to approach this the same way we did the last one. We're going to do it conceptually, and then we're going to do it mathematically. They always line up. Math just represents concepts, logical concepts. So, I approach this the same way I do inclined planes. This is like one of those inclined plane problems where you got to take an angle and you got to find another angle from it. It's a great time. Here's the thing: when I do these problems, I don't draw a bunch of arrows. I use a different logic. Is this more flat or is this more vertical?
More flat.
More flat. So I need to pick the answer. If y'all remember when it was flat, we had zero flux. So I need to pick the smaller of the options. If it's more flat, I should pick the one that lines up with it being more flat. So then you think about which of these is bigger, cosine of 20 or sine of 20. We know it's going to be an angle in there because it's at an angle and that matters. So which of these is smaller? Sine of 20. Which is cosine of 70. Cosine of 70 is smaller than cosine of 20. So this is the way I logic through these. It's much quicker for me. It's an option. It's not the only way of doing it. But this is what I use when I did inclined planes to kind of check whether or not my geometry all made sense and all that. Is it more flat or more vertical? And we call these the extreme cases as your checks. When you approach one extreme case, you should get closer to a certain value. When you approach another extreme case, you should get near another value. Which one are you closer to? Make sure your answer makes sense. All right, great. So the area vector here points up like this. The electric field points like this. Now you're like, how do I get, so this angle is going to be 70. I'm just going to tell you all that. How do I know that that's 70? There's a few ways you can do it. One of the things you can do is that this 20 degrees is equal to this 20 degrees. And you're like, how is that true? You got two lines like this. I think that's not quite right. Okay, let me erase that one. I drew that one not quite right. You got two lines like this. That's still, yeah, that gets us there. So this is 20, then this is 20. And then this angle here is my area vector. This is 90. So therefore, if this is 20, this is going to be 70. So there's ways to do the geometry and figure it out, but the quickest way, in my opinion, is you go with these extreme cases and it lets you logic through it. And yeah, sine of 20 is the same as cosine of 70. They're the same thing.
Couldn't you just like pretend your theta is the 20 and then just be like, oh, if you want the opposite, you use sine?
So you have to know that the angle between the electric field, well, have to. You need to know that the angle between, you know it's going to be either cosine of 20 or cosine of 70. After some point y'all do enough problems, you know it's going to be one of those options. How do you make the judgment call? You either draw the picture, and you can see that this one's bigger, you can visually see it, or you think the logic I did, or you do make some geometry. Yeah. So, yep.
But if we're choosing the smaller angle, then wouldn't we choose cosine of 20?
So not the smaller angle, the smaller value. Not the smaller angle, the smaller value. Sine of 20 is a smaller number than cosine of 20.
Is sine always smaller?
It depends where you are in the unit circle. Yeah.
Doesn't sine of 20 stays that way and cosine of 20 stays like that?
So it's unit circle, sine of 20, if you have a unit circle. So a unit circle, the x component of the unit circle is the cosine of it. The y component is the sine of it. So that's a separate thing. I can chat about that more. But if you just plug in a calculator, you'll see that sine of 20 is smaller than cosine of 20 as well. Yeah, it's a good question. It's good to know. All right, so now we're going to jump into Gauss' law. We're going to put all this together. What I taught you all is two things. This is what Gauss did. He took these two ideas and he put them together. He said the amount of electric flux is proportional to the charge enclosed. So we did that. We chatted about that. That was this whole problem. More charge, more arrows. Awesome. The next thing he did is he said, I can calculate flux. How can I calculate flux? By multiplying the electric field times the area, finding the part of it that line up. The more lined up they are, the more flux. The less they line up, the less flux. You got two definitions of flux. One proportional to charge enclosed, one proportional to E dot dA. They equal the same, they're both flux, so we set them equal to each other. So this is Gauss' law. This is what we're going to be using for the rest of the PowerPoint. Gauss' law says, this is just the flux that we did in integral form. This looks crazy. You're like, what is this little circle? It's an integral over the surface, because our surface can have different shapes and things like that. This is that E dot dA we just did. The E dot A we just did, that's what this is. It's just an integral form. So don't stress too much. And that equals the charge enclosed times some constant. 1 over epsilon naught is our constant here. That's what they discovered from experiments from Coulomb's law. And this is what we're going to be teaching you all how to use. And there's a few scenarios we're going to use it for. It's a very handy tool. Again, it actually is one of the 4 equations we use to describe everything. It's more general than Coulomb's law. Coulomb's law only applies to point charges. This applies to any number of charges. So the integral of E dot dA equals Q enclosed over epsilon naught. And something really cool here is even though I put an integral, we will actually not do any integrals in the rest of this PowerPoint. We will specifically choose shapes such that we don't have to do an integral. That's the power of this. We're going to choose shapes such that either the dot product is 0 or it's a constant. And then we don't have to integrate. You'll see what I mean when we start to do these problems. The only challenge to Gauss's law is choosing the right shape to make your little bubble. Choosing the right bubble, we call this a Gaussian surface. And determining the charge enclosed. That's the 2, as far as applying this, that's the 2 things I have to teach you how to do. And neither one is particularly challenging, especially because the shape, I'm just going to tell you what the shapes are and talk about why. And then this one, if you can do density, you can do this. This permittivity of free space I've mentioned before. It is a constant. It is 8.85 4 e to the minus 11 times 10 to the minus 11. This comes from experience. This is not theoretically determined. This is, if you all remember, I told you way back when, just to write this out, K equals, so K, Coulomb's constant, equals 1 divided by 4 pi, no, I don't want it to do that. Pi, oh, it's not doing it. Sad. Well, pretend like there's a pi here. Epsilon naught. I have a little macro thing on my computer that I'm using that like subs it in there for me. This is ugly, but K equals 1 over 4 pi epsilon naught. That's where the value comes from. If you just do the math and you solve for epsilon naught, you'll get 8.854. K is 99. And its definition conceptually is how easy or difficult it is to make an electric field in a vacuum. Cool. All right, so let's practice the right side first. Again, 2 skills. 1, how do we find the charge enclosed? 2, how do we choose the right shape? We're going to get kind of practicing both, different times, and then we'll put them all together to solve some problems. All right. Here's a picture. Again, let's see if the concept makes sense. I drew a random bubble. Who cares what the shape is? It's going to be relevant to figuring out this problem. It's this weird bean shape. What is the electric flux through the Gaussian surface drawn in the image below? So the image below, I got a bunch of charges. I got some positives, some negatives. They all have the same magnitude of charge. None of them are bigger or smaller than others. And mine says, what is the electric flux through this surface using that definition I just told you? Yeah.
But nothing's touching it. That only looks like
Nothing's touching it. So remember, so this is where you all have to make a decision. What side of the equation am I going to use? Am I going to calculate flux by doing the integral of E dot dA? Or am I going to find the flux by finding the charge enclosed and dividing by epsilon naught? Which one makes sense here? Is the flux 1q over epsilon naught? 1q. 2q over epsilon naught, 2q, or negative 1q over epsilon naught. All right, give you about 20 more seconds. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so we are definitely not going to do E.dA and do an integral because that would mean finding the electric field at every point due to every charge and then finding the area and no, awful. But we can totally just count how much charge is enclosed. I got 4 positives and 2 negatives. What's my total charge? 4 minus 2. It's 2Q. Great, that's my total charge. 2Q. And then we divide it by epsilon naught. Because that's how flux is defined, is you got to divide it by that epsilon naught. Yay! Why is it positive? Because I got more positives. If I had more negatives, it'd be negative. Easy peasy. This is the idea. How much charge enclosed in this shape? Cool. All right. This is another one. It's the same process. I'm just going to give you all the same. So this one's 0. I should have put the units. So this one I did bad in terms of the writing. So good thing I didn't ask it for you all. Newton meters squared over Coulomb. There's 1, 2, 3, 4, 5 positives. 1, 2, 3, 4, 5 negatives. So they cancel out. Yay. I'm not going to spend the time on this because it's the same as the last one. It doesn't offer too much extra benefit. Yay. More of the same. This one's just going to be 2 over epsilon naught. Yay. Awesome. Okay. Great. What's the point? I already mentioned this several times. Gauss's law lets us solve problems that otherwise would be very challenging. Very challenging. Like we're going to solve the electric field due to an infinite plane of charge. We're going to solve the electric field due to a line of charge, which we did last time, but required trig substitution. It took forever. We're going to solve it, and it's going to be super easy, no integrals involved. Awesome. We're going to solve it for a sphere of charge, and you can do it with a non-uniform charge density, though that might require an integral, but not for the reasons you might expect. And the last reason I mentioned it's useful is it's one of the 4 fundamental equations. With 4 equations, we can explain like all electricity and magnetism, which is nice. Nice and compact. So, I'm going to show you the 3 situations that we can use Gauss's law for. These are always the ones we use it for. They require symmetry because we don't want to do an integral. You could use this for problems that had like non-symmetry, but you would need a computer maybe to do some math for you. The following I'm going to show you are specifically chosen, and I'm going to talk through each one why they're chosen the way they are, such that we don't have to do an integral. They're all chosen for that reason. So, symmetry is great. It's all to make that E.dA integral go away. Here's the 3 situations. One is a line or a rod of charge. That rod can have thickness, doesn't matter, it doesn't change anything for us. So one can be a line or a rod of charge. One can be an infinite plane, or even it needs to be infinite. We need to have an infinite plane. And then the other one is a sphere. These are kind of a sphere or shells, some spherical shaped object. It could be hollow, it could be solid, doesn't matter. It could have a non-uniform charge density, doesn't matter. So I'm going to chat through each of these and why they work. It's a bummer that you're going to see a lot of finger painting. All we're trying to do here is make this integral go away. E.dA. We want that integral to go away. Now, I'm not saying I want it to be 0, because then you get nothing. I want to make that integral either be a constant, so I can just pull it out, or 0. So let's kind of chat through each scenario. So here I got a cylinder. Great. How is a cylinder beneficial to us? So when we're doing this integral, we're doing it over the whole cylinder. That means both sides. So it's got 3 sides to it. It's got this kind of wrapped around side, the walls of the cylinder, and then it has the top and the bottom. So we need to consider all 3 sides. You're going to see why that's going to be useful. So let's consider this part, that the sides of the cylinder. At the sides of the cylinder, this charge distribution, if it's uniform, which way does the electric field point? So this is a negative charge distribution. I'll let you all think about it. At point P, which way will the electric field point due to a negative line of charge? Think about it for a second, and then I'll tell you the answer. So a negative line of charge that's symmetric, if you all remember, the electric field is either, if it was positive, it'd point directly away from P. Because it's negative, it's going to point inwards. Negative, it's going to point inwards. Why is this useful? Which way does the area vector point?
The other way.
The other way, at every, or inwards, it really doesn't matter. What's the angle between those?
0.
No matter where you are on it, either 0 or 180, it doesn't matter. No matter where you are on this cylinder, no matter where you are on the side of the cylinder, the electric field and the area vector point the same direction or anti-parallel. Why does that matter? Because if they didn't, if the angle changes, you'd have to integrate over that. But because the angle doesn't change, awesome! We also know that the electric field everywhere on this surface is the same value. How do we know that? If you closed your eyes and I shifted things around, you would never know. If you closed your eyes and I took this like Gaussian surface and spun it, it's going to look exactly the same to you. Symmetry. Same thing. If I took this infinite line of charge and I shifted it upwards, you're not going to be able to tell. It's going to look identical. So everywhere on the side of this thing, the electric field is a constant. Why is that nice? If you have a constant and integral, you can pull it out. Now I'm just integrating over the area of the side of the cylinder. That's really easy. The side of the cylinder, you all can think about if you remember the equation for that. Great, so I got the sides done. Sides are awesome. Electric field is a constant. Area vector, just integrate, and the angle is a constant. The electric field is a constant. And the area is easy. The area of a side of a cylinder. All right, we got to look at the tops and the bottoms. The tops and the bottoms, what's going on there? At the tops and the bottoms, so this gets kind of funky. These are infinitely far away. But here, still, whatever, we'll say this. Which way does the electric field point away from a charge thing? So what's the angle between those? 90. So what's the flux to that?
0.
Great. We made the top and the bottom not matter. So we'll solve this problem later on in a later PowerPoint, but we basically made it so that this integral is just the electric field times the area of just the side. Great. That's one case. Now we're going to look at this one. We're going to look at the infinite plane of charge. Same thing. I want you all to predict. We're going to do the tops and the bottoms first. There is a top and a bottom. We care about both. Yeah.
Sorry, why is the electric field pointing away?
So yeah, let me label these. The electric field is pointed the same direction. Okay, normally I'd be writing this with this, but it is
I
weird.
went to the top.
Electric field's still pointing that way. Just like it was down here. Yep.
It's negative.
Yeah, you're right. I put it in the wrong one. This is the area vector. This is the area vector. Everything's worse when you can't write on stuff. Electric field points this way. Great point. So I should have this the other way. You get the same result, but that's a great point.
Well, I was going to say, was it from the top or a point down?
That's the area vector up there.
Oh,
Yeah. Slowly but surely, I'll get all these situated. Anywho, next one, still think through it. While I'm suffering through this, think about which way the electric field is going to point at point P.
For the second one?
For the second one, at point P, infinite plane of charge, which way do you expect the electric field to point at point P? So, this point, every charge on the right is going to point up to the left. Every charge on the left is going to point up to the right. They end up canceling out, so the electric field points straight up. So through the magic of copy and pasting, electric field points straight up. Suffering.
can you say one more time while it just points up?
The symmetry. The symmetry of all the charges on the right are going to make it go up left. All the charges on the left are going to make it go up right. They cancel out. Electric field points up. Hey, which way does the area vector point at the top?
Down.
You can kind of pick your poison. It goes up as well. What's the angle between them?
0.
0. Yay! So on the top, the area vector also points up. How nice for us. So the angle is a constant. Yay, up. On the sides, which way does the area vector point? Let's pick the right side. Which way is the area vector going to point on this right side?
Right.
If you all drew the area vector over here, It's going to point to the right. What's the angle between the electric field and the area vector? If the area vector is to the right, the electric field's up. Yeah, so this one's the exact opposite of this one. This one, we ignore the tops and bottoms, and we only care about the side. This one, we ignore the side, and we only care about the top and bottom. Great, works out great. Last one is the easiest one. We pick a sphere. Because if we pick a sphere, then the electric field and the area vector will always match no matter where you are in that sphere. So the electric field points this way, the area vector points this way, they're lined up. Awesome. At every point on that sphere, because of symmetry. Yeah?
Wait, but for the negative, shouldn't it?
They should point inwards, yeah. The electric field will point inwards. In either case, all we care about is that the angle is a constant. We do not want an angle that changes. So if we do some more finger painting up here. Reminder to you all that this electric field thing is E A. So it's the integral of E dot dA times cosine of theta. If that cosine of theta is not a constant, I can't pull it out. And I have to integrate, and that's miserable. So we have chosen 3 different shapes for 3 different geometries, and now we just need to apply it back to solve some problems. These are the geometries you'll choose due to symmetry. Some of them, it makes some of the sides equal 0, and some of them a constant. Other ones, it's just a constant everywhere. Yeah.
Why doesn't the P for the first one move inwards if it's negative?
It does. The electric field here is inward.
But not the P?
Point P is just where we're finding the field. I picked a random spot. Point P is just a random spot that I'm finding the field at. I said, hey, what's the field here? Oh, it points inwards.
Oh, is it the A that I'm getting confused with? The P? The A is going to the right.
That's the area vector. Point P is just a random spot I picked. Yeah, I can chat more about that in a little bit. Yeah. All right, so symmetry, yay, cool. All right, let's actually apply it, and this will hopefully, when we start putting in things, it actually be no numbers, quote unquote, but it's going to work out. And this one I can type out. It's going to be great, so I don't have to do too much finger painting. All right, a line of charge. On your paper, I want you all to draw the Gaussian surface for so I want to find the electric field at some point R. So there's my point R, some distance R from this thing. I want you all on your paper to try to draw the correct Gaussian surface, the correct dotted line bubble around it. What shape should I draw around this? That's going to be very important for solving these problems. Try it out. All right, so we refer back to this. We're going to choose a cylinder. Why are we choosing the cylinder? For the reasons I mentioned before and the reasons I'm about to tell you again. It's going to come up again. So great, we draw a cylinder. What's the radius of my cylinder? R, because makes sense, right? We're trying to find the electric field on this cylinder. This is a trick. Gauss' law basically is a trick that lets us solve complex problems. So let us write Gauss' law. Gauss' law says, through the power of copy and pasting as well, boom, E dot dA equals Q enclosed over epsilon naught. We're going to do one side of the equation at a time. And at the end of the day, what's the point? We're solving for E. We want to get E by itself. That's the goal of Gauss' law. That's the end goal. We're not charging closed is super easy. Area, all that, whatever. The goal of Gauss' law, the purpose for it is to find the electric field. So let's look at the left side. Just the left side. So, there is there is 3 surfaces on this cylinder. There is the side, there is the right flat side, and there is the left flat side. So I can kind of write that out a little funky. So we need to find Well, the 3 sides. So we're going to end up doing 3 integrals. So let's call this, boom, EA left side. This seems a little silly, but you're going to see what I mean. So we got left side, left flat side, I guess. Whatever, it's fine. An integral is just a summation. So we got this integral, we got this integral. Let's do the right flat side, and then we have the integral for the, I don't know what you call this at this point. It'd be nicer if I could say top and bottom, but there isn't. Let's call this the, something's hiding things. The rounded side. Sure. Rounded side. That's, the wrapping part of it. So, if you're like, what the heck is he talking about? This is the right, this is the, no, this is nothing right now. This is the right flat side. This is the right flat side. This is the left flat side. You can't see it, but it's there. And then the rounded side is, this whole thing, the rest. Okay? Cool. You're like, what is going on? This right flat side, I showed you on the picture before, the electric field points away, the area vector points to the right. You have 2 vectors that are perpendicular to each other. If you do the dot product, it equals 0. Boom, it's gone. The same with the other one, because the electric field and the area vector are perpendicular to each other. All we have left is this. And what's super nice about this one? The electric field is a constant. Pull it out of the integral. So, this whole thing then just equals E times the integral of dA. So, get rid of all that. And I believe in your ability to do this integral. What's the integral? Yeah, so it's just going to be E times A. E times A. You all need to figure out what that is. What's the area of that side? I'm going to clean it up so it's not as ugly. So try it out. Figure it out. See if you can figure it out. That's half the, if you can't do that, you're going to have a hard time. What is the area of the rounded side of a cylinder? Think about it for a moment. Alright, so here's the trick to this. A cylinder, this rounded side, is just an infinite number of circles. So what's the distance for one circle? Like if you want to find the circumference of one circle, what would that be? 2 pi r. And how many of them do I have? L. If this rod, we call this rod, how long? It's infinitely long. How long are we going to call it? L. What is L? Who knows? A big number. Really big number. So this electric field times pi, hey, it worked. Pi times 2 pi r. 2 pi r times L, where L is the length of this infinitely long rod. But you're like, what? How's that going to work out? Trust the process.
Why aren't we doing like area?
So it's the area of the rounded part of this, not the volume.
So we want to pi r squared.
Pi r squared would give you the volume of this cylinder. We want, imagine you took this paper and you wrapped it up into a cylinder. What's the area of this piece of paper? It's going to be just this outer part, and that's going to be 2 pi r L. All right, cool. Trust the process. So we're going to take this. We got one more slide I'm going to chuck this into. This equals Q enclosed over epsilon naught. That's the right side of the equation. If you're like, whoa, where did that come from? Gauss's law. We solved the left side. We set it equal to the right side. Cool. Trust the process. Solve for E. Get E by itself. So E equals Q divided by 2 pi r L times epsilon naught. All I did was move things over. And then there's one last step. One last step. This problem didn't tell us what Q was. It didn't tell us how long this thing was. It did tell us our charge density. It said we have some charge density of lambda. What is the definition of charge density, of 1D charge density? Reminder to y'all, lambda is Q over L. How much charge do I have divided by the length of the thing? Oh, look, a Q divided by an L. How convenient. So what's the long and short of this whole problem? E equals lambda divided by 2 pi r epsilon naught. And if you're like, so what? Why is this useful? We did this problem kind of, quote unquote, if I jump back, did I close it already? If you all remember, this was the electric field problem I helped you all with last week, where you had to do trig substitution to solve it. If we scroll all the way down to the problem we did last week, the infinite line of charge where I said find the electric field, this problem, look how much work we had to do to get the exact same thing. If you're like, what? This is different. 2 times k is the exact same value. Remember, y'all, k is 1 over 4 pi epsilon naught. If you sub it in, it works. Try it for yourself. So the question is, would you rather do this, or would you rather just do this, where we...
Can we just jump to, like, the rabbit side?
Huh?
Like, if you're doing this problem, everything, you just jump to, like, else.
Yep, 100%. Yeah, the question was, can I just jump to knowing I just need the rounded side? Yes, that's the goal. Once you do enough of these problems, you realize, if I have this type of problem, I don't care about the ends. But you have to, I have to show you all why we don't care about the ends.
So then would we get different kinds of problems where it would ask us to do the integral versus doing this method?
Yeah, great question. So would you get different types of problems where it says one is do the integral, one is do this type? Yes. So what this problem can't do, what Gauss' law can't do, is problems that don't have symmetry. So if I give you a charge distribution that's not uniform, you can't use Gauss' law for a line of charge. All right. Okay, so, great, look, there's the whole thing, yay! It's all there. In this case, though, they used the charge, they actually made the substitution earlier, and the L's canceled. Q equals lambda times L, you get the exact same result. L is infinite, but it cancels, so it's fine.
We just memorize and use that formula, or we have to...
So what you all are going to need to be able to do, if I give you all a Gauss' law problem, it's probably not going to be this one. I'm going to tell you that. What would I probably give you? I'd probably give you a sphere. A sphere is the most likely problem because you need to figure out how much charge is enclosed if I'm not enclosing the entire sphere. That's the type of problem, which I'm not going to get to today. All right, so this one just says plug in numbers. Like this is the same problem, but plug in numbers. So not very exciting. It's the exact same problem. I have a rod of radius 3 centimeters with a charge of -5. That's my charge density. It says find the electric field at a point 5 centimeter from the center of the rod. Okay, so there's a caveat here. If I gave you this type of problem, what I would give you is I would say probably find your electric field inside it. You're like, what am I talking about? So this point here, when I'm at a point inside of it, I'm not going to do this one right now for the sake of time, and I want to have my pen to solve it, so I'll relegate one of these to next class. The only real challenge for you all is finding the charge enclosed. Choosing the right shape and finding the area of that shape, it's based on the ones I just told you. Finding the charge enclosed is basically, we'll do an example next time and it'll be more clear. So, till then, let's just look at the plane for now. So we already did this, but let's see, I kind of chatted about this already, but let's see if it made sense. Hey, infinite plane of charge. What's the electric field at point P, some distance above the infinite plane? Is it straight up, straight down, down to the right, up to the left? All right, 10 more seconds. This should be easy peasy for y'all. All right, in 5, 4, 3, 2, 1. All right, reminder to y'all, for every charge here on the left, there's one that points this way. For every charge on the right, there's one that points up to the left. Their x components cancel, so it points straight up. Symmetry, it's great. Awesome. Okay. So, now we would solve this one. I'm going to run through this. I'm actually just going to look at the next slide where it's all nicely written out without me having to do finger painting. But I will remind you all what we're going to do is we're going to take those cylinder again. So I'm going to steal the cylinder. Boom. So we're going to chuck a cylinder on there. If I want to find the electric field some distance d away, let's pretend that that's way up here. So this is where I want to find the field, some point up at the top. Great, up there. Very, very important. There is a top of this cylinder, and there is a bottom that juts out the bottom. You cannot forget the other side. You're going to see why in a second. So we put the cylinder. Remember, this case, the sides, the flux to the sides is 0. Why is the flux to the side 0? Because the area vector points that way, to the right. The area vector points straight, or the electric field points straight up. Angle between them, 90, cosine of 90, 0. In this problem, we don't care about the sides. We care about the top, and we care about the bottom. That's what we're integrating over. Cool? So I'm going to jump down here, and you're like, oh my gosh. Here, actually, I'll just write it out. All right, so E times, remember, it's beautiful. The electric field everywhere at the top here is a constant, so no integration required. What is the area of a circle? Pi r squared. Awesome. So pi r squared. Great, that's the top. Plus E times, what's the area of the bottom circle? Pi r squared. Notice that there's 2 of them. This is the mistake that if you do, like this is the most common mistake. Equals Q enclosed over epsilon naught. Same exact thing. Nothing crazy here.
So 2e pi r squared.
Yep, so then you just, boom, 2. So E equals Q enclosed over epsilon naught times 2 pi r squared. 2 pi r squared. Cool. All right, one last step. We don't know Q. We know the charge density. Reminder, charge density this is a surface charge density. Q over the area. The area is pi r squared. So long story short, for an infinite plane, the electric field, and this is something that's super cool, and you're going to be like, how is this super cool? You'll see. Epsilon naught. All right, here's the thing that's crazy about this equation. Sigma is how the charge is distributed on the surface. Epsilon naught is a constant. 2 is a constant. Do you all see the variable d anywhere in this equation? So the crazy thing with infinite plane is the electric field is the same everywhere. Everywhere. Pick this point here. What's the electric field? Sigma over 2. If this is just a number, this whole thing is just a constant. You plug numbers in, there is no dependence on distance. The electric field is the same everywhere. Everywhere above this thing, everywhere below this thing, the electric field value is the same. Now above it points up, below it points down. The foreshadowing is an infinite plane is 1/2 of a capacitor. A capacitor is 2 infinite planes, one positive charged, one negatively charged. If you haven't heard of a capacitor before, we're going to learn about them in this class. They're in almost every electronic circuit you've ever seen. They are used to store charge, and in between them, the electric field is a constant everywhere. I don't care how close you get to one, how far away you get from one, it's a constant everywhere. So, we'll solve a couple more Gauss's law problems and then start talking about electric potential energy next class. And I'll have my pen, it'll be great.
Thank you.
Have a good one.